Okay. So yeah, grab a laptop. Everyone should grab a laptop today just to get us started. So this is the Circuits Lab class, where we will be putting into practice all of the theory that we learned in Engineering 12. This class has, anyway, it's a great class just because without this class, your knowledge of circuits is pretty much a mathematical, treatment, like learning calculus. What good is it? You can't really apply it unless you actually work with some real circuits. So that's what we are going to do in this class, and this class is sort of a mix. Today we're going to just work with FreeMat. But in general, we're going to be working with actual hardware components. I have a whole bunch of kits. A lot of you guys helped me put those kits together. Thank you very much for your time and for your offer, Oscar. Oscar's very appreciative. Yeah, so we've got a lot of things we get to play around with. The class basically involves us working with breadboards and multimeters. And we will be using some circuit simulation tools to kind of improve our understanding. And then we actually build circuits involving series and parallel and nodal and mesh analysis. All these things we learn in Engineering 12. And then some topics that are not covered in Engineering 12, like diodes and transistors, we'll play around with them a little bit just to kind of get, those are really fundamental, ubiquitous devices you should have some experience with. We also get to work with oscilloscopes, which is really fun. These give you ways of looking at dynamic signals and understanding what's going on in a time domain sense. We play around a little bit with microcontrollers, Arduino microcontrollers, because you can build a lot of circuits that interface to microcontrollers, and it's another way of applying what you've learned in this class. And we also cover complex numbers in a really detailed and applied way. So complex numbers will start to make sense to you as well, which is pretty cool. And we use that in understanding AC circuits. Towards the end of the class, we'll be doing some more extended applications, and there currently is a final product. I'm actually I want to put together like a midterm project. There's a few ideas I have along those lines, where you actually, pull together and do some kind of design work, kind of along the mid-semester. So again, design work is a really good way to kind of really absorb what you're learning, so these are not just empty theories. And I'll probably throw something out there in about 4 weeks or so. The final project is optional, and what I've done is given people extra credit for the Engineering 12 class, which is usually what people have the most problem. This class, if you just do the labs and you master it, it's hands-on. It's sort of kinesthetic learning. You want to be able to do good. Some people find this difficult. It's not easy for everybody, but in general, it's easier than doing circuit analysis. Although you're going to do some circuit analysis in this class as well. There's 4 tests, which are they're like lab practicals, just to kind of make sure you understand the basic lab outcomes. And so your grade is basically consists of 50% work, your lab work, and 50% on those 4 tests that we'll be actually having. So If you're doing this online, I even allow you to do the tests unproctored. The circuit class, you have to have proctoring for your tests. Those are much more challenging. These are really just getting you exposed to doing the hands-on operations. So it's a pretty short syllabus. I didn't include all the other stuff that the circuits syllabus has because it's kind of redundant. Are there any questions or anything about what I just went over? Okay. Pretty straightforward. Is anybody here registered as an online student? Are all of you all planning to be here in the lab each week? Okay. Okay, good. Because online students are given a circuit kit they can take home and do the labs at home with. In general, and I invite online students to tap in during the lecture, even if you can't be here in class, just because it's a good way to get help in real time. And another way for online students is to check into my online office hours on Sunday evenings and get help that way. So yeah, it doesn't have to be that isolating. It's much better to do this in a lab. Well, actually, you know, people have different minds on this. Some people have actually expressed, some online students have expressed that they actually kind of prefer doing the labs by themselves because they feel like they learn more. The lab environment can be kind of distracting with lab partners wanting to tell you about what they did last weekend and their plans. Yeah. Yeah, one person could take over, and the other person just kind of standing, you know, getting pulled along for the ride. We have enough circuit kits though that if you feel you're in a situation like that here in the lab, you can just let me know, and you can work independently if you want. It is up to all of you to master this, right? This is not something that, I mean, you don't want to show up in a lab at the university and not know how to do these things, because working with electricity is pretty important. And yeah, you want to know what you're doing. So gauge your learning, you know, and if you feel like, you know, your lab partner's not working out for you for some reason, you can find a new partner, or you're free to work independently as well. Yeah, there's a syllabus if you came in late. There will be a whole bunch of tutorial videos for people working online, so that is a thing that I will address. The first video from yesterday has been posted to the playlist already for those who are interested. You can just grab the playlist, and whoops, that's last year's playlist, which can be interesting, but let's update that link. When it comes to working with Circuit Lab, there are shared accounts, so you can access those. Some number of people can simultaneously access them. We don't want to overdo that because I don't want to raise any flags with Circuit Lab. It is possible for more than one person to use those. So we might just dive in. So basically, everyone needs a laptop. So if you came in late, grab a laptop. And yeah, Safni, Ali, why don't you guys grab a laptop? Yeah. But actually, the first part is a concept inventory. So this is a pre-test where I just want everyone to kind of run through a quiz, and it's a way for me to gauge how much you know coming into the class. And when we do our course assessments, at the end of the class, you'll get the same concept inventory, and this actually becomes evidence that I've actually taught you something. And it's actually very, very interesting. Last year, there was one student, there's like something like, I think there's something like 25 questions or something. One student started off with a score of 21 and ended with like 23. That student, like, I think really did great in physics and, you know, just really came in with a whole bunch of, understanding. And, I think they learned more, but as far as what the concept inventory showed, they didn't learn a whole lot because they already knew a lot coming in. And then like another student started in like with like an 8 and ended up with like a 21, which is like a huge learning, right? But people are all over the place. It's just sort of interesting to see what you get going into the class and what you get going out. And these are quasi-scientific instruments called concept inventories. They're not actually numerical problem solving, which is what the most of what we do in circuit theory class is. We're analyzing circuits. We're trying to compute something. This is actually just asking you qualitative questions about what you think is going to happen when circuit changes a certain way, or if you add a component or something. So to do this, and I need online students to do this as well, so online students don't blow this off. In fact, it's really important because we're trying to compare the learning between the face-to-face cohort and the online cohort and show that they're mostly comparable. So when you log into Canvas, you just click on Lab 1, and then the first link is the pre-lab concept inventory. And you can spend a few minutes doing that. It is optional. If you really don't want to do it, you don't have to. But I appreciate you do it. It's forms part of our research and assessment for the class. If you don't do the pre-concept inventory, you won't be able to do the post-concept inventory. And there will be extra credit for the post-concept inventory based on how many you get right. So there's an incentive on the post-inventory. There's no incentive on the pre-inventory. I don't care if you just click A for all of them if you want. But it is interesting if you do, I mean, don't do that, really. I'd like you to take it seriously. And yeah, so just go ahead and do the best you can. And when you finish, we will continue with the lab question. Any questions? No cheating. Thank you all for your effort on the concept inventory. Can't wait to see how you guys did. I'll let you know. So continuing, we are now going to do, oh, what is this class overview thing? Oh, I guess I am going to have a presentation I completely forgot about for class overview. There we go. Well, actually, this is good because you may have some questions about how the thing's going to all run and everything. And this is also probably helpful for the online students. Just to kind of give you a view of what's happening. What's interesting is when we started designing these lab activities through the grant that developed this and the materials class, if anyone took the online graphics class, those three courses are using materials from the CalSTEP grant that my colleagues up north and I have been putting together. And people have studied, what are you supposed to get out of a laboratory course? And this is a list of the 13 objectives. It's oddly screwed up in terms of the screen size, so I'll just show it like that. Basically, we're going to learn how to work with instrumentation, take measurements. We evaluate models. Circuit theory is sort of a way of, we create a bunch of models for how circuits are actually working. And we want to know if these models are correct or not. So we can build an actual circuit and take some measurements and see if the measurements sort of validate the You're supposed to be able to devise experiments, collect, interpret data, analyze data. This is where MATLAB comes in. This is a nice data analysis tool. Designing circuits, building, assembling, learning from failure when stuff doesn't work right, kind of debugging things, right? You know, a lot of people think, oh, it's just a lab class, but you know, these lab classes have a lot of really important outcomes. Not to mention, you know, learning how to be safe and communicating with your team members. There can be a little bit of ethics. I got to figure out a good ethics. Someone actually gave me some suggestions on an ethics example for circuits, and just being sensory aware. A lot of the rest of the engineering education can leave us spending a lot of time in our head thinking through various things. We can bump into walls and stuff and not really be paying attention to your senses. But when you're working with a real circuit, you have to have your senses turned on. So I initially was came up with this idea of kind of providing more simulation. You know, why not just do a whole bunch of, there's great circuit simulators out there, and we're going to get exposed to some of them. Why not do this whole class in circuit simulation? But a lot of students don't like that idea. So we actually are going to work with a lot of hardware. That's really the most fun part of the class. Even though you might, you know, find yourself getting stuck when it doesn't work right. And that's all part of the process, just sort of go with it. And then there's a whole bunch of studio videos. I've actually redone these. Rachel, a former student, was originally the one who did these, and I've kind of redone them myself. But you can basically get help a number of different ways. The circuit kit you're going to look at next week has all the components that you need to do all the experiments. Right, self-contained, which is great. It has this components case, which a lot of you guys helped me with. Thank you very much. It has power supplies. It has multimeter. It has a multi-instrument, which is a USB scope, and a waveform generator at the bottom, and an Arduino and speakers. We get to do audio experiments. Here's some circuits that people have constructed. Kind of a breakdown of the labs and what kind of modalities we're doing. You've been doing some work with, a lot of work with breadboarding and hardware, but some simulation. I've actually scaled back the simulation somewhat to actually have more hardware than my original intention. So there's some really nifty simulators. One of them is called Circuit Construction Kit, which allows you to simulate in a somewhat kind of quasi-realistic form, in the sense that you can actually watch the electrons flowing through the wires as your circuit actually runs, which is kind of helpful to kind of see that, especially when you have like a parallel circuit to kind of see which branch has the most current flowing through it. Really cool things like that. We're going to play around with that, not right away, but in a couple weeks. And then this is Circuit Lab. This is the circuit simulator I recommend. If you can fork over the $24, it's now $24, not $12 anymore. For 6 months, you can use that. You can also use the one that I've a couple that I've got for shared access. And we'll be using FreeMat today. This is an example of a script file that analyzes a really complicated AC circuit in the phasor domain, and this involves using complex numbers. This is a really challenging part of the course to actually solve without a computer, just because working with complex numbers is a pain, even on a calculator. It's just not very friendly. So we use FreeMat to make it better. You'll actually learn how to model a circuit in a simulator and sort of take measurements on the simulator and then build the circuit on the breadboard and also verify that, you know, the simulation results match what you see on your circuit reasonably well, and if not, you can kind of experiment or explore why. This is the Analog Discovery USB oscilloscope. It's a little pocket-sized device. This is the version 1. The version 2 is a little bit different form package, but it's the same nest of cables that come out of here. It does so many things besides what we use it for. If you do want to do your own final project involving something more complicated, there's a 16-channel logic analyzer, 16-channel digital pattern generator. It even has a spectrum analyzer in it. if you're interested in doing signal analysis, there's just some really cool stuff you can kind of play around Lab 13 AC measurements. I had a student who posted a lot of great videos, and apparently he took them down, unfortunately. So can't really show you these anymore. Jonathan Hall, he was really good. His final project was pretty impressive. What that is. Maybe you put him back up. Let's see. This video's unavailable. Yeah, he took all his videos down for some reason. I don't know why. Gotta bug him about that. For his final project, he did this personal alarm system, which is one of the options that I present in the final project section. And that was given to me at a conference I was at a couple summers ago, where these folks kind of explained, how students like doing these projects and how you can get credit for the circuit theory class, which most people want to get more credit for anyway. And what Jonathan did is he designed his own PC board, and he sent the design to China and got like you can pay like I think $50 or so, and they send you like maybe I don't know 10 or 20 copies of the board. So you get the benefit of scale. And he actually sent me one of them as a gift. So I have it in my office somewhere too. I should bring that in. But it was really cute. It was just a simple device that when you pull a pin out, like you can attach the alarm, and then you can attach a string to something you want to keep. If someone yanks this thing out, it sets off the alarm, and it makes this high-pitched kind of squealing noise. Very nicely done, and it's a great kind of capstone to the class. So anyway, that's sort of an overview of what we're going to be doing, and now let's go back to the lab, which is today's lab, which is this intro to MATLAB. This is the same handout I just gave to you in class. And when you're doing these labs, most week, you're going to have a data sheet to fill out. Now, for some reason, I don't know why, the way Chrome is configured, this data sheet is a Word document. And when you open it in Chrome, it wants to be able to help you edit it inside the Chrome browser. But people have actually messed up when they do that, and they actually end up, I don't know, they end up submitting a file that doesn't have anything in it. So obviously you get 0 points when that happens. So what you want to make sure is that you actually download it to your computer. So you can right-click on the link and say Save Link As, and download that to your computer so that when it opens, you're editing it in Word, not in like the Chrome browser. If it looks like you're editing it in Chrome, it's probably not going to be saving changes properly. So I wouldn't do that. And what you turn in at the end of the lab is the data sheet. The record of your work. And if you're going to work with a partner on it, please put everyone's name at the top so I can give credit. You only have to turn in one data sheet per team. And work like that. Put the date. And what we're going to be playing around with is FreeMat. And the lab actually kind of goes over a little bit about what we're going to be working with. We're going to be playing with FreeMat in a lot of different ways. You're going to be learning how to do all kinds of computations in FreeMat, everything from making a simple file to do a calculation of like the number of charges or something that go by in a certain time, to solving a system of equations in matrix form that you can use when the circuits get more complicated. I expect this is sort of a rundown, and you know, later on in the semester, if you really realize that you would need more computational help to solve a circuit problem, I expect you to be able to go back, and if need be, you can kind of pull up the lab again and just kind of get a refresher for how to use it. But it's a resource for you so that you can effectively use FreeMat, you know, throughout the semester. There is a download here if you haven't installed it on your laptop. Whatever, you can do that. You can also buy MATLAB for $99 or $50, I think, if you just get the stripped down version. Either one is fine. And another tool I mentioned is Octave Online. But let's start playing with FreeMat just to kind of show you what that's like. So this is FreeMat. It is a free version of MATLAB. And when you open FreeMat, you find this rather complicated work environment. There is a command window here, which is what the main display is. And then on the left here, there's a file browser, which kind of indicates where in your system you are currently pointing. There's a command history window, which shows you the recent commands that you or maybe someone else has typed on that computer. And there's a current list of variables and what they contain below here as well. So these are all part of working with FreeMat, and they all form the standard interface, and very similar to what you would actually see in MATLAB as well. So this shows you the current directory listing that you're in, and yeah, stuff I just went over. The command window can be used just like a simple calculator. So, and what I expect is you'll just sort of have the lab open and just sort of type in these things that are showing here. So if you type in 1.5, you're entering the value 1.5, and it stores it in a variable called ANS, which is short for answer. If you don't assign your answer anywhere, it just stores it in this ANS variable. So you can use this as a calculator, typing in arithmetic expressions. Remembering that the order of operations is such that multiplication gets done before addition, so that's 7.5, not whatever that would be, 9 if they would do the plus first, or I don't know, whatever. If you want to change the order of operations, you can put parts of the expression in parentheses, and that will force a different ordering. The key of working in MATLAB and other programming languages, this is a programming language, and MATLAB is actually not too far removed from languages like C. So if you've worked in a programming language like Java before, or taken programming in C, this will all be very familiar to you. When we normally work with complicated problems, we like to store information in variables. So you can make something like a variable called radius. You just say radius equals 4. And that puts a number 4 inside a variable called radius. And you can kind of see in your variable workspace the value radius here and its current value, which is 4. What's interesting about variables is you can change the values to something else. Later on, maybe you want to do a radius of 2. You can just set radius equal 2, and now that 4 has been erased with the 2 and been replaced. One really helpful way to think about variables when you're first starting out is that they are kind of like boxes. So when you say A equals 3, what MATLAB does, it provides you with essentially a box, and the box has a name, which is the variable A, or the letter A, the identifier, which is the name of the box. And then the box has a value inside it, which is, in this case, the number 3. So typically what programming has evolved is basically moving information from one box to the other until you can kind of calculate the desired result that you're trying to shoot there is a convention for naming variables, and they have to start off with a letter, and they can compose of letters, numbers, or the underscore character. And yes, but other than that, you have sort of some freedom in how you do things. Now, suppose you have a variable called radius, and another thing you could do as well, maybe you want to go back to the previous version of radius. Right now it has a 2 in it. There is an up arrow command on the keyboard. If you hit that up arrow, it will bring back the previous commands that you've typed. If you keep hitting the up arrow, you can go back and re-execute an older command relatively straightforward because of that nice up arrow. So it makes your life a lot easier in working with computational kind of steps. Now, you can calculate an area from a radius of a circle. It's going to be the variable pi times the radius, and you square that. And the symbol for squaring is the shift 6 symbol. And if you do that, you'll calculate an area of 50.265. There are other functions like the square root function, which will take the square root of 2 things. This is doing the square root of it's like a Pythagorean's theorem. If you want to if you have a right triangle with a base of 3 and a height of 1.5, you can take the square root of both of those numbers squared, add it together, and that'll give you the hypotenuse, right? So again, you can sort of type that out, spell that. SQRT is the name of a function called square root, and what we're doing is, the way functions work, as you're familiar with, you give functions arguments, and in this case, the argument is going to be 3 squared plus 1.5 squared. And when you hit enter, it calculates the square root of those 2 values squared and gives you the result. Now, each one of those results, if you don't specify what you want to store the result in, it puts it in A and S, but if you do specify a variable here, like something equals, it stores it in that value. There's a bunch of functions, common functions we use in this class, the trig functions, the logarithms, exponents, square roots, and so on. Those are all very useful. Another thing you can do in FreeMat is add a semicolon to the end of a computation. So if you type a calculation, just hit enter, it prints the result. If you hit a semicolon after the calculation, it still does the calculation, but it suppresses the result. It doesn't actually print it out for you. Which, when you're doing a long series of computations, a lot of times you don't want to see all the steps. You just want to see the final result. So use a semicolon to kind of just hide and not print out all those intermediate steps. The value is still calculated, though. So in your data sheet, you can now summarize the use of the semicolon in MATLAB. And I'll just sort of give you an overview and just let you continue. Well, although there is actually, let's just do part 3 together, just because working with a script file can be kind of tricky. And there are some people, like, gosh, I've taught this MATLAB, the Engineering 17 class a lot before. And occasionally I'll find people that they just never actually figure out how to do these script files. So this is a really helpful way of doing more complicated programs. So the way a script file works is a script file is a file in which you stick a whole bunch of MATLAB commands in, and it becomes basically a simple program that you can run over and over again and refine and fix and improve, make it better. And it's a better environment than just usually typing stuff into the command line. You can get away with that for a lot of this class, but when it gets really complicated, like towards the end when we do those really complicated circuits that have systems of equations and everything, you want to put it in a script file so that you can actually hang on to it better. So the question is, a conductor with a current of 5 amps, how many electrons are passing a point on that conductor in 1 minute? When you think about a problem like this, there's many steps involved. A good way to break it down is to think about what are the inputs to the problem, what formulas are you going to use to solve the problem, and what are the output that you should be calculating. The input to the problem is the fact that the current is 5 amps. For B, there's a formula for that can kind of convert, you know, well, we know the formula, right? I equals dq dt from yesterday, right? That formula for current. So we want to actually figure out what the charge is over a certain time. We got to integrate that current. So we got to essentially multiply 5 amps times however many seconds are in a minute, 60 seconds. And then however many coulombs are in an amp, right? So we have to actually, well, one coulomb is in an amp, but how many charges are in a coulomb? Because we're actually trying to figure out actually how many electrons are passing that point in time. So eventually we're going to produce essentially a number of charges. So that's sort of the problem solving step. And now we're going to start formulating the solution in FreeMat. And there is a recommendation that before you get started, it's a good idea to clear out the variable workspace by typing clear. You can think about why that would be helpful or not. It's going to wipe out all the variables that you've currently defined so that you don't accidentally use a value that you might have defined in a previous calculation. So to clear the variable workspace, you notice you can kind of check out the variables over here. We currently have ANS, and hypotenuse, and radius, and area. If you type clear, all those variables go away, although you still have the ANS variable. That's sort of a default that you're always going to have. If you want to get rid of the command line, there's a CLC command, which stands for command line clear, and that will wipe out all those instructions taken to the top. David? What if you want to undo a command like clear? You can't undo clear, unfortunately. Yeah. So once you wipe it out, what you could do is you could redo those calculations over again. You can't restore it without redoing the calculations over again. And yeah, so it's a good question. I'm glad you guys are asking this. If you go to the history window, you'll see all those commands that you just recently typed. So for instance, if you want to redo that again, you can just click on the radius equals 4 and maybe grab that and the hypotenuse one, right? You want to maybe redo those calculations all over again. You just highlight those like you're selecting some text in a document, right? And then you can say right-click, copy selection, or just execute selection, and then it will just run those for you. So that is a way to recover something that you might have accidentally erased. And now you've got your variables all over again, so you can decide if you want to clear them again, right? So you type clear. And then they go away again. Yeah, no, you can't do the CL, undo the CL. Yeah, these are just wiping things out. You can't really undo those. So think before you clear. So just to kind of play around with this, we can solve this first just in the command line, and then we'll actually develop a script file so you can kind of see how that works in comparison. So the question is, you know, how many charges are flying by when you have 5 amps going through a wire? How many charges are flying by in a minute, right? Well, the current equals 5, right? That's 5 amps, and we know that the Coulomb constant, you know how many charges are in a Coulomb is 6.25 times 10 to the 18. So we put the E18 there. That's scientific notation in FreeMat. If you ever see that E in a result, that just means times 10 to the 18th power. And that defines the Coulomb constant. Now we can make a variable called, like, say, charges per second. Notice we're using the underscore to cascade and have multiple names in a variable, multiple words in a variable name. And that's going to equal current times Coulomb, right? Because an amp is a Coulomb per second, right? If we multiply coulombs per second times coulombs, right? Get that right? Question? No, do I need to put a space between the equal sign and the rest of the expression? You don't have to, but it makes your work a little clearer. Yeah. So you can do unit analysis, but if we do current times Coulomb, that will tell us how many charges per second are flying by. And if we want to calculate how many charges per minute, we could just take that result and multiply it by 60. Oops. So if you hit enter, you're going to get, there's 3.125 times 10 to the 19 charges per second. And then you can take charges per minute, and that's going to equal charges per second times 60. So it's a pretty simple problem, and we solved it relatively quickly. And that gives us the answer, but it's using the command line, which is okay, you know, for simple problems, you know, it's okay. But it is better in general to get used to using a script file for your work. And the way you can make a script file is you can select all the statements that you just typed in the command history window, and then right-click and choose copy the selection. And now we're going to paste that into a separate file that we can then run again later. So we just typed all those commands in here, right? And you don't want to take it from the command window, but from the history window. So here's the current equals 5, you know, Coulomb equals that. Oops. And charges per second and charges per minute. Grab those 4 statements, and then you're going to right-click and say copy selection. Sorry about that. So command history, highlight those 4 statements, right-click and say copy selection. And now we've saved those, and we're going to make a new file to put that in. So there's a command in the file menu. It says file, new file, and you're just going to click on there, right-click, and then paste those statements. And that gives you a script file. The thing is, though, before you save it, you really want to make sure you know where your file pointer is pointing. It may be pointing to a place where you don't really want to put your files. So there's this current directory pointer. I generally like to put that on the desktop because I know I can find that pretty easily. And like when you want to turn in your work, it's kind of convenient to have that all on your desktop. You could also maybe put it in the downloads folder, like your data sheet right now. When you download it, it probably got stored in your downloads folder, so that would be another place you might want to put it. But to actually change the current directory pointer, you click on this yellow folder icon right here, which says choose directory. And this will allow you to navigate to a place. And this is the place where we were going to put it, which is it's buried inside our program files folder. It's kind of a stupid place to put things. So you can click on the desktop icon. And if you don't have a folder, you might make a folder for engineering 12L or 12 lab if you want, and open up that folder. And then we can, that is the folder, and we're just going to select that folder, and then that becomes the place that our file is pointing, our file browser is pointing to. Did I do that too fast? You want me to do that again? Okay. So the way it works is you click on the manila or that yellow folder icon, click on the desktop, make a new folder, click on the new folder button, and call it something like, you know, lab folder or whatever. And actually, you don't even need to go into it. If you just hit enter, it has highlighted that, and it's going to make that your default folder. So this thing should say the same folder you just created. You just click on select folder, and then that will go into that folder. I'm going to go to my engineering 12 lab folder, which like that. Everybody got that okay? Well, it didn't save anything yet. It just moved our file pointer so that we're actually pointing to a folder on our desktop. Now the file itself is still waiting for us to save that. And once we've pointed to the place that we want to save it, we can call it the script file example1. So when you save it, it's going to save now in that folder. And so we're going to say in the file menu, where it currently says untitled, you're going to say file, save as. And now you can see it's pointing to our desktop engineering 12L folder. And we're just going to call this example1. Okay, it's a little bit of work, but once you do that, you can then execute your script file anytime by clicking this green triangle, like a play button. When you click that green triangle, it runs your script file and shows you the results right here. It also tells you the source here, which is the example script file that we just created. That's how you use a script. Yep. That doesn't sound right. I'll come around and more.
Yes, so
That's a good step.
Now, if you change it, you change cool, man, thanks. How's he bubbles? Wait, why is that not noise? I'm gonna let you figure that out. Was I there? Well, those things go back to was that pretty little? We had to introduce ourselves. How was it? Does it seem difficult? Not right now. It's very. I don't know how this was going to be, really don't. But our first class was just talking about binary next steps on workers that are changed. But I left. When you press that, that's the so it's online on Canvas. It says that it's worth something like how hard did you guys get? You're already here. You might be
Our second is also in trouble. No, you're not there.
Yeah, I was thinking about it. That's our program.
Good. Very good. Yeah.
I'll tell you what, though, his explanations are way cool.
Okay, so that's the basics. It's a bit of a headache, but once you get the hang of it, it makes your life a lot easier. And you know, you can limp along without using script files, but you're going to look like a bozo when you go transfer. And then once you have the script file, which is kind of nice, is you can re-execute it pretty easily. Like, suppose you want to know, well, what if I had 10 amps of current? Well, you can change the 5 to a 10, right? And then you re-execute it, and now you have the new results for when you have 10 amps. So that's the advantage of working with script files. It makes it easy to re-execute and modify and work in that environment. Now, it's not good to turn in something that doesn't have a lot of explanation, so that, you know, if you just turn it in the way it is, it'll be a little bit mysterious about what this thing is actually doing. So what we do in FreeMat is we add comments to our scripts. And this allows people, including you, later on to read your own script and understand what actually you were doing. A lot of times you're the person that's going to be benefiting from this more than anybody else. So it pays not to be lazy. So what we do is, to make a comment at the very top, click up there and hit enter and make some space. You can add a % symbol. The % symbol turns the text red, and it makes what's called a comment. The rest of the line is ignored by FreeMat when you run it. It doesn't execute those statements, but they're there for us to put notes to ourselves about what this program is actually doing. it's a good idea to put your name there as the author. And a description about what this thing is actually doing. It's calculating the charges per minute not per second, flowing through a wire. And it's sort of helpful to also sort of break down the problem in terms of what's the input. Well, the current, and let's just set this back to 5, say. Maybe I should make my font bigger, huh? That's kind of small. So that's our input. You can also decide maybe maybe I don't need to see the output for current, so I can put a semicolon there to suppress it, right? And it can also be helpful to indicate that this has a unit of something like amps here, because we can read that later. And this is again, I'm going to put a semicolon here because I don't need to see that. And this is some number of electrons, number of charges in 1 coulomb. So we can then have a section maybe called intermediate calculation. Which is the charges per second, and then maybe the result. This is actually doing a lot of extra typing, but it is making our work more readable, kind of showing us what we're actually doing. And the semicolons, you might put all, in front of all the statements except maybe the last one, so that all you see is the final result when you're done. So that's something that now becomes presentable, that you can actually put in your data sheet and show your work. So you would basically copy this code into your Lab 1 data sheet. So at this point, now that you have it in a nice form, you can highlight it all, say copy, and then you'll go to your data sheet. And then we put our example 1 script right there. Want to be fancy, you can indent it a little bit. Using the right arrow up there. Okay, so that is your first step. So that's a big hurdle, and I think once you get scripts done, you should be okay. I think from here on out, you should be able to do the rest of this on your own. Calculate the mass of water in a cylindrical tank, make a script file called question 4 to do that. Then you're going to get to play around with vectors and arrays. A vector is a list of numbers stored in a single variable. This gives you the opportunity to make larger data sets and analyze them, making plots and so on. Doing calculations with those, plotting data. Shows you a plot here. You can pick those plots and put them also inside your data sheet. Solving systems equations. and then a word problem. So that's basically it. So just finish that on your own, and I'll come around if anybody has any questions. I think you're all in pretty good shape at this point. Just keep building up your answers in the data sheet.